In part 3, we'll further extend some of these concepts to the global scale. One way that the magnitudes of phosphorus sourcing and utilization throughout the global food system is shown on this graph, which is called a phosphorus flow diagram. Starting with phosphate rock in the upper left, the size of the arrows scale with the global annual mass flows. For example, and as we saw earlier, many million metric tons of phosphorus is mined from phosphate rock annually. Most of that phosphate rock is used to produce phosphorus fertilizers, which are used in agriculture, which is captured by the larger white box in the middle. To the right of the agriculture box, we see the phosphorus flowing into the food processing sector, after which some of the phosphorus goes into landfills, and some, about 3.5 million metric tons, enters the human diet. In the lower right, we see that both human excreta enters surface waters, which can be associated with the innate inefficiencies of some wastewater treatment facilities at removing phosphorus. We also see another large arrow of phosphorus flows entering surface waters, which is coming from the agriculture box in the middle. A lot of this flow is from runoff from agricultural lands, which was mentioned near the end of the previous section. This diagram is useful for quantifying phosphorus flows. For example, we can see that of the 18 million metric tons that enters the global food system, only 3.5 of it enters our diet, which is only 20%. Much of the remaining phosphorus that enters the food system ends up in landfills and surface waters or locked in the system somewhere, like becoming strongly bound to soils such that it cannot be used by plants. As a final point, we see that humans are a relatively small component of the phosphorus flow consumption diagram, but it's our human decisions that influence the entirety of the phosphorus flows shown here. Not just our diets, which we'll talk about in part 4, but also decisions in policy and business, for example. In part 2, we looked at the global distribution of phosphate deposits throughout the world, and we referenced geopolitical factors that are relevant, such as national policies and laws, international trade, and international conflicts. The graph shown here shows the historical price of one type of phosphorus fertilizer called diammonium phosphate over 2 decades, from 2002 to 2022. In 2008, there was a large price spike that was due to strong global demand for fertilizers and low fertilizer inventory. Significant price changes can have significant negative impacts to businesses, particularly small businesses and small farming operations. Then, after a period of relatively predictable prices, the prices started to climb again around 2020 and accelerated in 2021 when China stopped exporting fertilizers to other countries, and then again at the outset of the Russia-Ukraine war. This price volatility of a key crop nutrient is a reminder of how geopolitics and economics are intertwined with food security in our increasingly interdependent world. The negative consequences of losing phosphorus to surface waters is a global problem. In this graph, we see what's called the water pollution level for phosphorus, represented by colors from red to green. Red and orange colors represent pollution levels above 1, which means that the phosphorus pollution is too much for the water basin to handle. This means that harmful algal blooms are more likely because of the availability of phosphorus as a nutrient for algae. Note that in the US, Europe, and India, as examples, are covered in orange and red. To contrast that, there are areas of the world where surface waters are not polluted with phosphorus, like parts of sub-Saharan Africa. And rivers containing phosphorus pollution will eventually flow to the coastlines and oceans, which brings us to what is called coastal dead zones. A coastal dead zone or a hypoxic zone is a term used to describe regions of coastline waters that have too little dissolved oxygen in the water to support marine life. Marine life in the area of a dead zone either dies or, if they can, they'll leave the area. In these dead zones, marine habitats that would normally be full of life become biological deserts. While dead zones can occur naturally, they're also created or enhanced by human activity, including phosphorus pollution originating from human sources, human needs, or human actions. The map shown here shows us the distribution of scientifically reported accounts of coastal dead zones inventoried a few years ago. Note the large number of dead zones on the eastern and southern coasts of the US, as well as around Europe, correlating with the water pollution levels for phosphorus we saw earlier. These zones also correlate with what is called the human footprint, shown in colors, which is a representation of the impacts of human population on the environment, which is influenced by population, their consumption habits, and their impacts. Note here the warmer colors of red and purple in the eastern, southern, and midwestern US, as well as throughout Europe. From this plot and the previous one, we see correlations between populations of the past, water pollution, and coastal dead zones. And this brings up an interesting question, which is, where is population growth increasing the most in the future, and will these problems repeat themselves? And that brings us to population projections from the United Nations. If we look to the past, from 1950 to 2000, we see Europe and North America as a dark red line. Some increase, but not a lot relative to faster growing populations in Asia. If we look to the future, we'll see population growth in Asia plateau, whereas population growth in sub-Saharan Africa will continue to explode. By 2075, which is easily within the lifetime of those born today, the population of sub-Saharan Africa will outnumber all of the other regions of the world. Just as we saw in the US starting in the 1940s, the demands for food in this region will increase, which will increase the need for phosphorus fertilizers made from phosphate rock. By default, with our current technologies and phosphorus management strategies, these increases in phosphorus inputs come with consequences of surface water pollution, harmful algal blooms, and coastal dead zones. As we move toward this new world population, it will be important to learn from our experiences of the past decades and create innovations in phosphorus sourcing, utilization, recovery, and recycling so that we can continue to feed the growing human population.